Now let's look at mixture properties. This is just going to be a very brief introduction to mixture properties. But first let's look at gases. If I wanted to use a mixture of several gases, perhaps it's for a combustion process, but it could be for any reason that I've got this mixture of gases. And I wanted to be able to analyze a problem with a mixture. I need to understand a little bit about how they behave. Now, there are several different ways that I can do this, but I'd sort of like to be able to use an equation of state, something simple, ideal gas-like, and I need some ways to do that. So one of the things that people do is they use the compressibility factor, the Z equals PV over RT, as a way of estimating properties of this gas mixture. But in order to tell whether or not it's a good ideal gas, whether I need to modify or not, I need to be able to use the compressibility chart, which requires me to know TC or PC. So K's rule was developed, and it's not too bad. It's not awesome, but it's not too bad. What it says to do is take the critical temperature of each of the substances. Maybe I have a mixture of methane, ethane, and propane. So I'll use the critical temperature of the methane times the mole fraction of the methane, and the critical temperature and mole fraction of the ethane, critical temperature and mole fraction of the propane, and that sum will give me an estimate of the critical temperature of the mixture. I can do a similar thing for the pressures. Now, it is important that I use mole fractions in these calculations. So this is called K's rule, and once I have this estimate of TC and PC, I can use it to calculate a relative temperature and pressure, temperature over this TC, pressure over this PC, and go to the generalized charts and look up a value of Z. This is most often used, but there are a couple of other ways people have done this, and they say that, well, the pressure effect of each chemical should add up to give me the total pressure. So if I look at something called a partial pressure due to each component and play a little bit of algebra games, and again I'm leaving that part out, then if I calculated Z for each component at temperature and volume specified, multiplied by the mole fractions, then that will give me a good estimate of the Z of the mixture. Or I can say that the volumes should add up. The volume of the ethane, the volume of the methane, the volume of the propane should each add up. And so if I do Z holding P and T constant, then multiply by those mole fractions, that would give me an estimate of Z. Most often what people do, since all of these are loose approximations, they'll just choose one, whichever one seems easiest to them at the time, and either work with that knowing that they've got a fairly large error introduced, or another technique is, if you want a little bit better, is they do all three of these and then come up with an estimate of Z and then take the average of those three and say, there's my value for Z. None of these are going to be awesome results, but when you have simple gas mixtures where the materials are fairly similar and therefore the gas mixture is well behaved, they really are not too bad. Now I next want to talk about partial molar properties. A partial molar property is how the property changes in a mixture if I add a little teeny tiny bit more of one particular substance. So let's take that methane, ethane, and propane mixture, and I have 30% of methane and ethane and 40% propane. And I'm now going to add an extra 5 molecules of methane. How much does that affect some property? Maybe it's the volume, maybe it's the enthalpy, whatever. How does that affect some pressure? So if I hold the temperature and pressure constant and hold the amount of all the other molecules constant. If I just change one molecule, what does it do to some variable? And that's called a partial molar property. Now, a partial molar property is going to be different than what it would be for the pure species. But if I look at the difference between the partial molar property and that same property for the pure species all by itself, okay, times the number of moles I have for all the different things, I would get the mixing property of that substance. Okay, so this is probably just like whirling in your head right now, all these crazy names and crazy nomenclature. But this is easiest to think about. This isn't a really great example as far as the thermodynamics is concerned, but if you were to mix a cup of sugar and a cup of water, and you put both of them into a measuring cup and stir them, you don't end up with 2 cups of material, right? And that shrinkage is the volume change of mixing. Now, unfortunately, that's not such a wonderful explanation in terms of thermodynamics because you had all that airspace in your sugar, okay? However, and this is a little bit smaller quantity, but if you have pure alcohol and pure water and mix them, they mix very nicely, but they shrink a little bit. Okay? I also am going to have changes in all of these properties when I mix 2 species. And that change in the property with mixing these 2 pure substances is going to be the property change of mixing. Okay? Enthalpy change of mixing is one that is particularly interesting if you've taken a Chemistry 1 lab course. Okay, you were told probably when you mix acids and waters that you always add acid to water, not the reverse. Well, this chart here, I know it's too tiny to really read, but this is the enthalpy versus the composition change, where over here is strong acid and over here is pure water. And if you'll notice, these are different temperatures along here. And the temperature increases and the enthalpy goes up. But look how close together these temperature curves are. If you've ever mixed your acid and water incorrectly, you probably, because I've done this, I know, you experience a fluid that basically comes to a boil in your hands, in this beaker in your hands. So you're holding your graduated cylinder, whatever you're doing the mixing in, it suddenly gets incredibly hot, and so the natural reaction is to drop it, and now you have broken glass, spilled acid, boiling spilled acid. It's a horrible mess. Their instructions for always add acid were oh so correct. The correct thing to do is if you are over here where you've got water and you're adding a little bit of acid at a time, you're coming across here and you do it nice and slow. The temperature goes up fairly slowly. You have time for that heat to dissipate. But when you're coming across here, going from acid and putting drips of water in, notice how tightly clustered these are. It heats up instantly, and there's no time for the heat to dissipate. So you've experienced partial molar properties. You just may not have realized that's what you were doing. One last little topic is chemical potential. Again, we're going to be needing this for a topic later in the semester. Chemical potential is the partial molar Gibbs energy. Okay, so recall, G is H minus Ts. I said it was sort of like how we defined H is U plus PV. Well, G is H minus Ts. It's the Gibbs energy. And if I want to look at the partial molar Gibbs energy, the effect of adding one molecule of a new species into my mixture, this is the partial molar Gibbs energy, and it's the chemical potential. Now, naturally, it's a function of T and P, meaning that the math is simplest if I work with temperatures and pressures. Okay, And so that's part of why this is used, but this chemical potential is going to be very important when we talk about phases and equilibrium. Okay? So this is going to come back for us later. So chemical potential is designated as a mu. Okay? Mu of species I is the partial molar Gibbs energy of species I, which is how the total Gibbs energy changes if I change one molecule of N, okay, of species I, holding temperature, pressure, and all the other things constant. Now, a lot of times we relate it instead to something called fugacity. Fugacity is an F, and fugacity and chemical potential are related to each other. And that's really about as much as I want to say about those at this point in time. But these are some words that we will come back to as we talk about phases and equilibrium.